Hello everyone. We are going to solve some problems in the chapter 3 for exam 1. So problem 20, a world-class sprinter accelerates his maximum in 3 seconds. Oops. He then maintains this speed for the remainder of a 100-meter race, finishing with a total time of 9 seconds. What is the runner's average acceleration during the first 3 seconds? So in this case, we are going to divide two time frame. So that's from 0 to t1. So let's assume that there's a velocity. And then we are going to see that it is accelerated for 3 seconds. And then after that, maintains this speed, remainder of a 100-meter race, finishing with 9.7 seconds. Okay, T2. So this is the thing we need to think about. And then the question is, what is the acceleration, which is the slope for this case. So let's summarize what are given. The total distance is 100 meters. Accelerate for T1, 3 seconds, as we have seen there. And then runs at a constant speed. Okay, so speed does not changes. And total time is 9.7 seconds, such that the cruise time from here to here is 6.7 seconds. Okay. Start from the rest, okay, equal to 0 here. Accelerated during the first 3 seconds is uniform with the average acceleration A. So this is what we are going to concern. And then we are going to write the kinematics for each phase. The end speed after accelerations, so Vmax is AT1. So it is slow is A. And then, as you can see here, AT1 is Vmax. Okay. And distance covered while accelerating from here to here. We note that S1 is given by this formula. Note that initial velocity was 0. So that's the reason we have this one. But initially, we have S0 plus V0t plus AT squared. But we start with the origin. We start with at rest, so that this term is gone, so that we have this formula. And distance covered while cruising, so S2 from here to here. And then you get S2 is given by Vmax time to T2. Okay. So here, T2 is actually, this is the T2, I'm sorry. This is T2. So from here to here, it has a constant speed. So note that what we are doing is that from 0 to T1, we have a constant accelerations. So from T1 to T1 plus T2, we get constant speed, okay, Vmax. So that S2 is given by S2 is the distance covered by while cruising, we get the S2. is given by constant velocity times duration of that speed. Okay, is given by this one. So that we now know S1 and S2 should be 100 meter. Also, the sprinter is running 100 meter, so that we know what the S1 is, the accelerating zone. S2 is the cruising zone with a constant speed. And then this will satisfy 100 meter. And then if you take out AT1 here, then you get this relationship. And A is, what we need to know is what the A is. Okay, A is given by these parameters. And we know that T1, T2 is given by this relationship, so that we can find out A. Okay. Note that the unit should be the meter per second squared. And when the sun is directly overhead, our eagle flies toward the ground with a constant velocity of a certain kilometer per hour at 58 degrees below horizontal line. Calculated distance is shadow traveled on the level ground in 12 seconds. So that what is happening here is that the sun is here, and then here's the eagle. Let's say I was mean that this is the eagle, and then it is below the horizontal line. So we have a 58 degrees, and then it is constantly cruising down with the velocity is 13 kilometer per hour. And then note that what is the shadow? Shadow traveled on the level ground. That means that it is above the overhead, so that we have a shadow, and then it will be shadow for 12 seconds. Okay. So what they found out, what we need to find out is that this horizontal directions that is covered by the 12-second flight. Okay, so let's try to summarize what is known. Speed of eagle is this. Direction is 58 degrees below the horizontal, and the time is 12 seconds. So sun directly overhead, sunlight is vertical, the shadow's motion on the level ground equals the horizontal motion of the eagle. So this part. So this is the kind of a key to note that how the natural language distance, its shadow travel on the level ground is now changed into horizontal motion of the eagle. That is the it, hurdle you need to overcome. But anyway, once you note that the horizontal part is now given, you can decompose into vertical motions and as well as horizontal motions. But in this case, we are only looking at the horizontal motions. So that's the things. So first of all, the velocity is now changed into meter per second. And then horizontal component of a velocity, this part, is if this is the v, and the horizontal part is this one, and then we know what that angle is, 58 degrees C. And this is nothing but cosine, right? So that we get this velocity. And then distance, the shadow travel is Vx times the t. We know what the horizontal velocity, and then the time is given already, 12 seconds. So that distance is going to be this distance. Okay. A metal key is dropped down from the bridge. When it passed by a height h is 41 meter, its speed is 19.5 meter per second. How long after this moment the key will hit the ground? The gravitational acceleration is given by this one. So that once again, it is a constant acceleration motion. Constant acceleration motion. So let's assume that this is the starting point. And then, so note that this is from here, from the ground to this is initially h is given by 41 meter per second. And it is drop. It is under the influence of a constant gravitational accelerations. Okay. And note that initial velocity is also given. V0 is 19.5 meter per second. So let's assume that this is the positive directions. So we have h is known, v0 is this one, and the gravitational acceleration is in the same direction. So everything is in this downward. We are going to take it as a positive and find out the t to hit the ground from that instant. So downward is now as a positive sign. And then we note that distance is given as a function of a t here. So note that the initial position S0 is taken account as a 0 here. Okay. And then 41 distance and the initial velocity and your constant gravitational accelerations is taken account, and then we get equation for t in terms of t. And then you need to solve the t using the formula for the root, finding the root. And then you get this value, and then after calculations, you will have this seconds. So once you find the t, then you can check whether it is satisfying the 41 meter height. So if you just put the t into V0 t plus t square, and then you just plug in this t here, and you will get 41 meter, which is correct. And motorcyclist heading east through a small city accelerates after he passes the signpost marking the city limits. His acceleration is constant. At time t equals 0, he is 4.5 meter east of the signpost, moving east at 40 meter per second. Find his position with respect to the signpost at t equal to 3 seconds. So in this case, we need to summarize what are the initial conditions so let's say this is the eastward, so that we have a x0 initial position and initial velocity. So we have x0 and v0, okay? And then we need to find out its distance after t equal to 3 seconds, while we are assuming acceleration is constant. And then we have to use, once again, constant acceleration position formula, so that x is given by this one. So we know what the x0 is, we know what the v0 is, and we know what the a is. And then we just plug in t equal to 3, okay? And then we just 3 here, there. Then if you just add them all together, you get this value. So this is the direct application of this constant acceleration position formula here. But you need to identify what are the givens: initial position, initial velocity, and acceleration. A motorcycle heading east through a small city accelerates after he passes a signpost marking the city limit. Once again, his acceleration is constant, 4.3 meter per second square. At time t equals 0, he is 5 meter east of the signpost, moving east at 16 meter per second. Find his velocity at t equals 3. In comparison to previous case, problem 29, we need to find out the position, x. But in problem 30, we need to find out velocity. And then we need to use the constant acceleration velocity formula like this, okay? And then we know what the V0 is, we know what the A is, and we just plug in the t equal to 3. And then we get this velocity. A motorist is traveling with a constant speed of about 80 meters per second passes a school crossing corner where the speed limit is 10 meters per second. So obviously it is over the limit, right? Just as the motorist passes, a police officer on a motorcycle standing at the corner starts off its pursuit with the constant acceleration of a 3.6 meter per second square. What is the officer's speed at the moment he catches up with the motorist? So that we have a two object. Previously, we have only single object. So we have a motorist, and it has a constant motion, constant velocity, Vm, which is 80 meters per second. And the officer has a constant acceleration, A. And obviously, initially, so we have, this is the constant velocity, and this is the constant accelerations. So write the position as a function of times such that for the motorist, it is constant speed, so that xmt is given by this one. So here we have assumed that at the signpost, we set x equal to 0, at t equal to 0. Okay, so that it doesn't have x0 here. So that we have xmt, motorist position is given by constant speed times t. But the officer, it starts from the rest. Note that police officer on motorcycle standing at the corner starts off. That means initially at t equal to 0, we have officers, the police, so let's say this is the P. And then we note that the police officer was 0 at the same position as the signpost. And we note that VP is also 0, okay? So that utilizing this acceleration position formula, we note that is given by this only the acceleration take part, okay? So that we have this one. And then there's another very important things. What do we mean by catches up? So police will catch up with a motorist. When it means catch up, so it will have a same distance. That means That means catcher means police position and the motorist position is the same. This is the how to describe the catch-up, the natural language, into our physical model. So this is the very important step. If you don't have these equations, and then you cannot get the T. So anyhow, the police officer will have a constant acceleration motion such that it's a quadratic. And for the motorist, it's a constant speed, so that it's a linear in T. So that if you get the equal sign here, then you get this one. So that you get T equal, you see that T equal to 0 or T equal to 10. T equal to 0 means, well, of course, they were at the same position. X equal to 0, T equal to 0. Okay? So this is the what we get. But after that, after 10 seconds, they will have a same position once again. Okay? So once we find out the T, then officer's speed at the moment is VP is given by AT. And then you can just plug in the A and T here, and then we get this one. And the distance at T equal to 10 seconds, motorist travels 18 times 10, 180 meters. And the officer, you will get this, and then it is the same position. So in other words, XP, T equal to 10 is XM, T equal to 10. So it catches up. One kind of airplane was to reach a speed before takeoff at least 29.3 meter per second and can accelerate at this one. So speed and acceleration is given. What minimum length must the runway have in order for airplane to be able to reach this speed before takeoff? So that it starts from, let's say, T equal to 0, and then we have a x0, and then v equal to 0 initially, so that you get this one. And then what we need to have is that we need to have v is given by 29.3 meter per second. And during this time, we have a constant accelerations, 2.2 meter per second square. And then we need to find out the distance s. Okay? And then we know that for the constant acceleration kinematic relation, we have a very useful equation for finding out the relation between velocity, acceleration as distance all together. Okay. And then it is not it is not related with the time at all, but it is just initial velocity, final velocity, and the constant acceleration and the travel, the distance. And then from this, you can find out this one. Note that V0 was assumed to be 0, so that we get this one. And then plug in the number, velocity is given, and then you get the v square, and a is given, 2a is given, such that s is given by this number. Okay. Now let's check out the case. So the time, we did not consider any time here. Then t is velocity over acceleration, because v is given by at, right? So v0 was 0. which is 0. And then you get the time is found. You need this velocity with this acceleration, and then the time is given. And then if you just plug in the time into distance, the average velocity, and then you will get the same distance as this one, okay? Okay, that's it. And I hope you could understand the very basis of the one-dimensional motion with the constant accelerations. Thank you.